Hello guys, this is Yash Khanolkar and today I'm going to demonstrate DLIC experiment 3, which is on the design of a practical integrator circuit using op-amp OP07. Now in a practical integrator, the output voltage is the integral of the input voltage. Now we go into the LTSPI software and we check the schematic of practical integrator. Now in this circuit we can see that we have R1 and C1 and R2 in parallel with C1. Now, in an ideal integrator, we don't have this R2, but in a practical integrator, we do because when the frequency is very less, this C1 can get open circuited, which can lead to a very high open loop gain and which can lead to saturation. And the values of this R1, R3 we can find through a calculation, which we have shown here. So we take two frequencies, FA as the 3 dB down frequency and FP as the 0 dB frequency, which are depicted in this diagram as FA here and FP here. Now we assume a capacitor CF and take a capacitance value which we can use in this experiment, and we can find the value of RF and R1 by this formula as 15.9K and 1.59K respectively. Now we have to give two supply voltages, VEE and VCC, which we give as 15 volts, and then we give a sine input here with DC offset as 0, the amplitude as 1, and the frequency as 100 hertz, and an AC amplitude of 1, and a transient time of 0.01 seconds. Now we are ready to simulate this diagram, and we check the V in, we check the V out, and we can see that the gain is almost 10. And we can also do this for a higher value of frequency. We can do this for 1K. Okay, and run, and we can see that the gain has dropped down a little bit, but it's within our expectations and it's relatively high. And we can see that the output voltage is inverse of the input voltage, which is expected because we have given the components on the inverting terminal of the amplifier. Now we can increase this to 10K, and now we simulate, and we can see that the gain has almost dropped to 0. We have to zoom this. Yes, we can see that there is no gain at this point, and this is the 0 dB frequency uh, value, so we don't expect any gain. And so this is what we can do if you have a sine wave input. Now we can also give a square wave input. So for the square wave input, we need the transient time to be 1m. Okay, we don't need this sine wave. Instead, we have to take a pulse. So we go to pulse. We want V initial as -1. We want V on as 1. We don't have any time delay. We want the rise time to be 0.001 mu. We want the fall time to be the same as the rise time. We want T on to be 0.05 m, and we want the time period to be 0.1 m. Okay, so we just drag this down to make it a bit clearer. Yes, and so we simulate this circuit, we run this circuit, and we can see a square input here, and for a square input we get a triangular output. Now we can see a slanting triangular here because of the capacitor takes some time for charging, but after stabilizing we get a smooth triangular wave right here. So you can see a smooth triangular wave as an output to the input of a square wave. Now we can input a triangular wave also. For that we just have to change the pulse values, and We can put pulse values of 0.05 m as rise time, 0.05 m as the fall time. This should be taken as 0 and 0.1 m. Yes. So now you can simulate the circuit again. Check V in. You can see a triangular wave here. You can check V out. We can see the charging time of the capacitor, and we can see a smooth sine wave as the output right here. So this is what you can do if you get a triangular wave as an input to this practical integrator. Now one more thing which you can do is to find the frequency response of the circuit. to, so to find the frequency response we don't need a pulse, so just delete this. The transient response should not be there. Instead, it should be AC analysis, and the type of sweep we choose is decade. The number of points per decade we choose is 1000. The start frequency is 1 and the end frequency is 100k. Okay, so we simulate, we run this. So we see the V out here, and we can see that the practical integrator basically acts like a low pass filter which allows the lower frequency to pass through with while clamping the higher frequencies. And this is the wave which we expect for the frequency response, while this is what we expect for the phase response. And we can see the 3 dB down frequency 1 kilohertz here, and the 0 dB frequency 10 kilohertz as being exactly 0. So this means that our practical integrator is working perfectly. And this is it guys for the video, and I hope you like the video. Thank you.